Hello, can you hear me?
Yes, sir.
Yes, sir.
Start the class now.
Okay, sir.
So in the last class, we discussed until Python object-oriented programming. Today we will start from here. So in Python, if we want to define a class, we use the keyword class. We use the keyword class and then the name of the class, the colon, and then the indentation. So after the colon, this indentation defines a new block. And we have another def here, that means another function and another new block. Now, this function here, its name is underscore init. So double underscore before and double underscore after. And the name is special init. So it's a kind of keyword. And this is the constructor of this class. So basically, the constructor is the init method. And also there is a specialty in the signature of the class. For the argument list, the first argument, a positional argument, is used as a this pointer. So if you remember in C++, especially in C++, we use a this pointer. So basically this pointer refers to this own instance. So we can think of it recursively. So the very class code that we are interacting from, the memory address used by that class, if we want to refer to that memory address, we use this pointer. Now in Python, there is no this keyword, even there is no self keyword. So basically this is agreed upon name among all the programmers, but Python, what Python cares is the first argument. So if we use if you write ABC instead of self and then use abc.name, the things will work without any warning, without any problems. So only the first argument, the position of the first argument, it matters, but the name doesn't matter. But normally Python programmers use the word self to refer to this pointer. So in summary, the classes in Python, we start the class with keyword class, and then we can define variables inside the class. Like here we defined one variable, species, and it will have class scope. The init method, it is the constructor of the class, and the self pointer normally refers to the instances of this class. So that's why we see that for the class scope variable, we just defined the variable, but inside the init method, when we define instance scope variable or instance local variable, we used keyword self then a dot. So basically these variables, they'll have instance scope, their class or their object local variables. Now to initiate or create an object of a class, we do not have to use the keyword new. We just use the name of the class and then the arguments. Now if we check, here we're using argument 1 and argument 2, but when we define the constructor of the class, we had 3 arguments: self, name, and address. 3 arguments. But when we are calling this class, and we are trying to instantiate an object of this class, we are using only two keywords, 1 and 2. So we are not passing the self pointer. Basically, compiler takes care of that. Compiler knows the address our object will use, and compiler will pass the address with the self pointer. We don't have to worry about it. So if we want to access any variables or any functions from the class, we can we can call that using the created object dot the name, maybe the variables or the functions. So in Python, we can declare only one constructor. So we can think of it as a limitation, but Python was not designed to be robust in this respect. We still can initialize the classes in many different ways. So we can use one init method, and inside the yes.
স্যার কয়েকজন স্টুডেন্টস আর ওয়েটিং এ আছে, জয়েন করতে পারছে না।
Hello.
Hello. So we can think that only the facility to declare only one init method, it's a kind of restriction. It's okay, but we still can initialize the class in many different ways. We have to use one init method, but inside the one init method, we can have many if-else or many different blocks, and many different blocks can be used to initialize different states of the object. So yes, we can use only one init method, but still we can initialize the class in many different ways. So it's not a limitation really. So classes can declare either instance attributes or variables. So basically, attributes or variables, or class attributes or variables. For example, here we are declaring two class variables and two instance variables. Now we can check there is a small code here. So we are creating two objects, and we are calling set age method. So we are calling this method, and we are setting self.age with the value passed in when we call this function. So for P1, we are trying to set the value of self.age to 10, and for P2 it's 23. Now the problem is we have one class variable. We have one class variable age, and then we have instance variable age. So we're creating any variable instance variable age here. Now, if we want to print, we'll see that this print line will print 10, and this print line will print 23. Basically, we are printing the instance variable. Now, if we want to print the class variable, we can just write person.age. So class variables are declared outside of any methods, but inside the class block. Inside the class block here, and we declare the instance variable with self dot then the name of the variable, self dot then the name of the variable. Now we have two different attributes or variables, class and instance. So to access those variables or attributes, there are three kinds of methods: instance method, class method, and static method. So there are different kind of methods to access different kinds of variables. Now the instance methods, they can only instance methods, they can only access the instance variables. obviously. The class methods, they can access only the class variables, and the static methods, they cannot access any instance variables or class variables. They normally use the namespace only. So for example, if we think about if a mathematical function sine, cos, or getting a constant like pi, so we think in math context. So we think that they will be defined under some math library because it's logical. On the other hand, to calculate this function, we do not need to use any state of the class. So for example, if you want to calculate sine or cos, it's just a function. We provide the inputs, we get the outputs. So it's logical they will be under math library, but it's also logical that they will not have any internal states. So for such methods, we use those methods as static methods. So basically, they are using the namespace. Now to define different kind of methods, we can just
স্যার ইনস্ট্যান্স মেথড সেটার মানে এক্সাম্পলটা কি হবে, মানে ইনস্ট্যান্সের ভ্যারিয়েবল গুলা কি হয়?
So we can pass any
ইনস্ট্যান্স, ক্লাস, স্ট্যাটিক, মানে তিনটারই স্যার ভ্যারিয়েবল যে ডিক্লেয়ার করব। সো এই ভ্যারিয়েবল গুলা মানে ইনস্ট্যান্সের ভ্যারিয়েবল গুলা কোনগুলা বা ক্লাসের গুলা কোনগুলা একটু বলতে।
So instance variables are here. We have some examples here. For example, here. So whatever variable we declare outside of any methods, for example, here variable 1, variable 2, they are class variables. So they have class scope. So if one object of some class changes this variable, other objects will see the changes. Now, if we want to declare instance variables so that they remain local to the objects, we declare them using self dot then the name of the variable. And we can declare them in any methods. It's not that we only need to we can only declare create them in init method. It's not true. We can create them in any instant methods. For example, we had another example here, age. So we see that this method set age, this method created a new variable self.age. So this variable was not created inside self init. You see, inside init we only declared name and address, but inside set age we declared a variable age, and this is an instance variable, and we can check it from here. We are changing the value of this variable. We are changing the value of this variable, but these changes are reflected in the instance variable, not on the class variable. So that's why this print will print 10, this print will print 23, because the changes are object local. They are not reflected on the class scope variable. Is it clear?
Yes, sir. Okay.
So if we want to declare instance method, it's the normal methods of classes. So we just write def and then the name of the method, and the first argument should be self, because if it wants to use any of the local object local variables or instance variables, it needs a self argument, and then if we have other arguments. Now for class method, we need to use a decorator class method. Now the first argument of any class method, we are writing as CLS. Normally programmers write it CLS, but also it is not a keyword defined by Python. The position is only important like the self, but this pointer only has class scope, not the instance scope like this. So so this type of methods or instance methods, they will be able to create instance variables. So instance variables means they are object local. Whenever we have a new object of the class, they will get a local copy of those variables. They can change, modify, whatever they do. Those changes will remain only inside that object's memory. Objects from the same class will not see those changes. But whatever methods is declared inside these type of methods, whatever variables, they will have class global scope or class scope. So if any of the objects changes these variables declared here, other objects of this same class will see the changes. And static method, they don't have any this pointer because they cannot access any of the instance variables or the class variables. They are here only to use the namespace, so that we can call myclass.static static method. So it's not here for any interaction with the states of the class. So we already discussed what is instance method. So it's just for reading. Again, class method, what we mean by class method, we already discussed. It's just for reading. Similar for static method. Now, what is the difference between static method and class method? So I hope it's clear now that static method, the main difference is class method can access the class scope variables, but class methods, they cannot access the instance scope variables. Static methods, on the other hand, cannot access anything. Basically, they cannot access any state of the class.
একটা কোয়েশ্চেন ছিল।
Yes.
So লাস্টের যে স্লাইডে ছিল, যখন স্ট্যাটিক মেথডস ডিফাইন করা হয়, আমরা কি অ্যানোটেশন গুলো মেনশন করতে হবে নাকি?
Yes, yes, you have to annotate the static methods like this.
মানে উপরে ওই অ্যাড ক্লাস মেথডস লিখতে হবে, রাইট? মানে দিতে
Yes.
হবে।
Yes. There are some other
Okay.
ways too. So it is one of the method, one of the way. So I think 3.9, Python 3.8, they changed some of the things, but we still can use that. So was that your question?
জি স্যার।
Okay. And if you annotate the classes with appropriate like names, it becomes easier for future modification. So whenever you see the class, you understand that this is a static method or this is a static class method. So even before checking the code of the class, we know what it can do. So it's a good practice. And I think until Python version, I'm not sure, but until some version of Python, you could get some error because static methods has no positional arguments, but class methods has at least one, and they have different semantics, like what this pointer can do and can do or cannot do. There are some differences. So if you do not annotate them, you'll get some errors. So inheritance in Python, normally in Python, Python supports multiple inheritance. And also we can use other object-oriented programming concepts from Python. For example, this is the slide to understand what do we mean by parent-child and what do we mean by object-oriented programming. It is mainly for self-grading. So for introducing the concept of inheritance, we'll use two classes. The first one is polygon. Polygon means it will have some sides, that's all. And we want to define another class, triangle, which is a child class of polygon. So polygon, we know that triangle class, now it can inherit from polygon. So if we want to declare that to Python, so we basically give as a parameter the name of the parent class. So this is the child class. So we are using kind of parameter list to declare the parent classes. Now to call the init method or any other method of the parent class, we can write the name of the parent class, dot, and then the method that we are calling from the subclass or the child class. This is one way, but if we do that, then we also need to pass the self pointer. Another way is to call super dot. So if we call super dot, then we do not need to pass the self pointer. We can just provide the argument list. So that's how we declare that this is a child class.
So 3 টা কি বুঝাইতেছে?
This is
Sides.
just number of sides because it's a triangle. But the main thing is here we can use either this construct, polygon dot name of the method, then self, then 3, or we can use super dot name of the method, and we are not using the self here, just the 3. So 3, we are trying to pass an argument that we need 3 sides from the polygon class because it's a triangle class. But that in this slide we are trying to show that in this construct, if you use this construct, we don't need to use the keyword. Now this is a class diagram, another homework for you to translate it to Python code so that you can practice the object-oriented programming concept with Python. To declare multiple inheritance, it's simple. We just use the parameter list type initialization. So this is a derived class, and it is deriving from base 1 and base 2. So yeah, just it can even use more classes. They will be just comma separated. That's all. Now to use a inheritance of structure like this, so here derived 1, it is from base 1. So derived 1, your parent class is base class, and derived 2, it's using derived 1 as the parent class. So basically we are providing the name of the class, similar to function argument. Operator overloading is important for Python because we want to use Python as a mathematical tool. So whatever class we define, they may use some of the operators in different ways. So we need to know how to define operators for a class. So it's easy. In Python, the compiler provides us support. The support is more like, it looks more like API support. So if we want to use some operator, we need to implement specific type of functions in the class. For example, if we want to define a point class, and maybe we are defining just this code. Now the user of this class, the users may think that we can add, because normally we can add 2D points. So it's defined, we know how to do it. But if we define a class like that, in this class there are no hints that we may use it we may use the plus operator for the objects of this class. But the users, they may accidentally use it, and then we'll get an error because we did not tell the class how to interpret this plus operator, and this is a user-defined object type. So if we want to declare it to the class, normally we use add underscore add function. So here there are two underscores. So this method, we need to define this method. And if we do that, then the objects of this class, like point P1 plus P2, compiler will not throw any error. Compiler instead will use this method to find the result for this. And we see that this method will be called for P1. So whatever is the whatever object we have in the left side, so it will call like P1.add underscore add, and we know the self pointer for the memory address for object P1, and the other will be P2. So then this function body will calculate self as P1 and other as P2, and it will return the result. Now we can use almost all of the Python operators. So there is a partial list for that. If we use plus, internally it will be translated like this, and we need to implement this function. So if we have a user-defined class that does not implement this method, then this operation will throw an exception. Similarly, if we want to want that our the objects of our class can use the minus operator, then we have to implement this method underscore sub underscore. Similarly, for any of the operators, if we implement this method in our class code, then the users of the class will be able to use these operators. So this is the last slide of Python class, Python programming. So I know most of you, if not all of you, already are familiar with Python. I just wanted to discuss so that everyone, if accidentally someone does not know Python, he gets familiar with it, and also for other people who already know Python, for them it's kind of brush. So do you have any question? If you don't have any question, then I'll start discussing. I think today we'll discuss nearest neighbor algorithm, and then we'll discuss some concepts from probability. Do you have any questions? I think there are no questions. So today we shall start discussing our first machine learning algorithm, the simplest machine learning algorithm, in fact, the nearest neighbor algorithm. So this is really simple, and we really do not need to build any model, or the training is basically storing. So we do not go through any training loop or any training process. We just store our historical data, and that's all. When we need to infer something, or when you get a query to classify something, then we do a simple matching. That's all. So even if we the operation or the total process is so simple, the accuracy of this algorithm sometimes sometimes is much better than some of the complicated algorithms. So you need to learn it. And also it's pretty easy to implement and to learn. So we'll discuss this algorithm with context, with examples from MNIST digit dataset. I think some of you at least are familiar with the dataset. So it's a dataset of handwritten English digits from in fact many people. This dataset we can download it from MNIST website. So this dataset has, I think, around 70,000 examples. 70,000 examples mean 70,000 images like this. So the dataset contains images and also the labels. So this is the image and this is the label. And it contains, there are some more examples here. We can easily understand that this is an instance of 0, 1, 2, 3, 4, and so on. Now we know that we have many statistical methods to solve this problem. But during even 80s, people tried other ways. For example, using some geometry, like what should be the shape of 0? How can we define a range of shapes that we use for describing a single object? For example, if we can define the shape inside 0, people will write 0 in many different ways. But if we can define the shape inside 0, and that is flexible enough, then we will be able to use that concept to detect 0 in handwritten digits. People tried that for many years, but people failed because there are so much variability in people's handwriting that if we want to like list them all, it will be like writing lots of rules and then maintaining lots of rules, and still new rules will come up again and again. So that's why we need something from statistics, not something we can define with algorithms. So if we look at the data set, we'll find examples like this. Now here, some of them are easy to understand. Some of them are really hard to understand. For example, this digit, this one we can say 4. This one we can say 4, but any system can misclassify it as 9. Similarly, this 4 or this one, this number. So you can say it's 2, or some classification algorithm can detect it as 3. So there are some easy examples, there are some hard examples. And in MNIST dataset, there are 60,000 images that can be used as training set, and there are 10,000 images that can be used as test set. So training set means we can use them to train our model, and test set means we can use them to test our model. So first one is to train our model, and the second one is to test our model. So training means we train the model. Then what is model basically? So model basically contains some numbers. It's a statistical algorithm that can capture variability. Now with these 60,000 images, somehow we give it to the model, and model understands the variability, and it can capture the variability. And then based on that, it can produce labels. Then we use the test set to get some labels. We already know the labels of this test set. Then whatever model gives us, we check with what we know. And then we can find out accuracy and other metrics of this model. So basically, when we say model, we're talking about a statistical model. A model means it has some numbers like knobs and other things. Those numbers can capture the variability of any data set. So how do we classify a new image? For example, we trained with all these things. How do we classify the new image? Basically, for nearest neighbor algorithm, we compare. Now the question comes, what do we compare basically? We'll see that we compare the numbers that represent these images. And then based on that comparison, we return a label. So how do we really do it? We do it by comparing the numbers used to represent these images. Now the question comes, how do we represent these images? So basically, these images, they have different specific sizes. For example, a list has images of width of 28 pixels and height of 28 pixels, and it's a grid. Basically, it will have something like this: 28 columns and 28 rows. Now these, so that there are in total 784 grid cells here, and each cell contains a number between 0 and 255. So it's an image of size 28 by 28, and because it has only one channel, that means it contains a grayscale image. It contains a black and white image. And 0 to 225, the numbers, 0 represents the black, and 255 represents the white pixel value, and in the middle, they represent from white to gray to black values. For example, this pixel, it's a gray pixel, it's almost black, and it's a black pixel. So this pixel will have almost all of them will have value closer to 255, and these pixels, sorry, closer to 0, and these pixels will have values closer to 255. So that's how we represent an image, our data set. Our data set will also contain, for the test set at least, and also for the training set, because it's a supervised training algorithm, it will contain a label like 3. So for each image, there is a label, this is 3. For another image, there will be another label for that image. Now, when we want to apply nearest neighbor algorithm, we need to apply some operations on the numbers. So these numbers in the grid. So how do we do it? We can do it in two-dimensional structure, but to make everything simplified, we unmarshal that 2D structure into one-dimensional structure. So everything, the calculation becomes easier. It's not that we cannot do it in 2 dimensions. We can do it, but things becomes complicated. In 1-dimensional, things are too easy, very easy. That's why the first step is we unmarshal the structure. So how do you unmarshal the structure? So we know that there are 28 rows and 28 columns here. So we take row number 0 or first row, and we write here maybe these first 22 numbers. So this first row is coming here. Then the second row from the left. Then the third row from the left, and so on. And in this way, in the original image, there are 28 by 28 pixels. That means there are 784 pixels. Only we unmarshal them. Each image is converted to a 1-dimensional array of 784 pixels. Clear? Any questions? Okay, so I hope you understood. Now we'll do it for all the 60,000 images. Now we already talked about that. We do not really go through any learning loop or learning process. So basically, representing the data, we are done with the learning. Now, if a new instance comes, so we need to classify a new instance. What we do, suppose we get a new instance. This image, 3. This 3. Suppose we are getting this image new 3, and we want to classify it. Then what we'll do, for the new instance, we'll do the unmarshalling process again, just for the new instance. There will be around, not around, exactly 784 pixel values here. Then what we'll do, we'll find the distance from this number to this number, from this number to this number, from this number to this number, until the end, this number to this number. And then we'll find maybe Euclidean distance or something, some distance, d1, with this image, and we'll do it for the new instance. So this is the new instance. We'll do it for all the 60,000 training images. So basically, when you get a new instance, we'll find 60,000 distances to all the images that we have in our database. And then we'll pick the label for the image that has the shortest distance. For example, if we have a if we get a new instance of 3, we'll find the distance with all the examples in our database. Maybe we'll find a distance with 1, maybe 12K. With this one, maybe we'll find a distance of 16K. Maybe with this 3, we'll find a distance of maybe 0.2K. Something like that. So when you are done with finding distance with all the examples we have stored, hopefully we'll get the shortest distance with an image containing 3. And then we'll return 3 as the label for the new instance. So basically, this is nearest neighbor algorithm. Now we need to talk about distance a little bit. So what is Euclidean distance? So Euclidean distance, basically, suppose we have 2 points, 1, 1, 7, 7. Now, if we want to find the Euclidean distance between these 2 points, what we do, we find the distance. Suppose this is 2-dimensional coordinate space. We find the distance in 2 axes separately. So this will be 6, this will be 6, and the distance will be described as 6 squared plus 6 squared. So that's how we find Euclidean distance. It is mostly used for nearest neighbor algorithm, but we can sometimes we sometimes we have to distance other. We have to use other distance metrics or methods. Now for this problem, the MNIST digit classification problem, we need to use 784 dimensional vectors. We saw that the one-dimensional unmarshaled vector they have 784 dimensions. So basically all the 28 rows, and the rows contain 28 numbers. So basically 28 by 28 equals 784 numbers, and we have 784 different numbers to represent an image. That means our data set has 784 dimensional vectors. Now here X is one image, numbers for one image, and Z numbers for another image. So for example, if we have a stored image, we call it maybe X, and the new instance, we call it Z, and then we take the difference. That means we are taking the distance in that axis. We are taking the distance in that axis, corresponding axis, and then squaring up and adding up all the numbers, and then taking the square root. So basically, we are taking the Euclidean distance in 784 dimension. Now, so what we are doing basically after getting a new instance. So for example, here we have 60,000 training images and 10,000 test images. So in that case, what we can do, like taking the test images 1, 2, 3 until 10,000, and for each of the images, we can calculate 60,000 distances with all the test images, and then take the label that has the shortest distance, and do that for all the 10,000 images, and then find the accuracy. So what is the misclassification rate? That means for the test images, maybe the actual level is 2, and we are getting the shortest distance with 3. So it's a misclassification. Maybe for test image 2, we had level 3, and we got shortest distance with these 60,000 images with an image with content 3. So it's correctly classified. So we do this for all the 10,000 images. Then we find accuracy. Accuracy means basically here misclassification rate, 1 minus misclassification rate. So correctly classification rate. So the actual content of the image is 2, we're getting 2. So it's correctly classified. Actual content of the image is 3. Our algorithm is returning maybe 4. So it's a misclassification. We keep counting, like for how many instances from these 10,000 instances are correctly classified or incorrectly classified, and then we divide correctly classified divided by total number of images, and then we get the accuracy of the algorithm. Now, if we do that using this nearest neighbor algorithm, I don't know why the slides are not showing. Do you see any content of the slide?
No, sir.
Actually, the content is there, it's not showing. Okay, let me reload the slides. So can you see this content now?
Yes, sir.
Okay, so we want to find out how accurate is our classifier. And if we do that, you will find that this simple algorithm has accuracy of almost 3%. Misclassification error rate of almost 3%. That means accuracy of almost 97%. So given that we really do not need any training process, just need to like reformatting the storage or unmarshaled the 2D structure into 1D structures or one-dimensional vectors. The performance is not bad, 97% accuracy almost. And in this case, the training error is almost training error is zero. Training error is zero. So by training error, we mean what is the error we get for the training data. So if we have a robust model, later we'll see that when we'll use statistical models. When we train the model, we still get some error during the training process. Now, if we get zero training error for a model, it's really bad. That means the model is memorizing the data, and later we'll have a variance issue. But for nearest neighbor algorithm, the very nature of the algorithm is like that. We do not get any training error because we really do not go through any training process. The training means the images are stored in one-dimensional vectors with some labels. That's all. So there are no possibilities of getting any error. But we get test error. So when you use a test set, here we use our test set up to 10,000 points. And for those testing points or test examples, we are getting 97% accuracy. That means almost 3% error. But it is not really a bad result. Now we checked some of the errors that we got. For example, the next when we use this example, it returned a level for 4. Now we can see that it may be 6, it may be 4. It's very unclear. So even for human eye, it's a difficult problem. Now these two for human eye, it's not a problem. But obviously, we cannot say that the machine learning algorithm is terrible if the algorithm labels it as 0, because already there is a partial 0 here, and also maybe it's very close to 0. So we see that even this simple algorithm, it performed really good, and we can easily explain the errors. It's not that the error is so funny. It's not like that. The error, in fact, looks like that the errors are logical. But still, we want to improve the performance of the algorithm. Now, how can we improve the performance of the algorithm? So the most intuitive and obvious way is to increase K in nearest neighbor algorithm. K means with how many neighbors do you test? For example, if you use K equals 1, that means after we get the distance values, maybe T 60,000, we sort all the distances and we take only the top distance. K equals 1. That means we are considering only the nearest one neighbor. Now we can change that. We can change K to any odd numbers and then take a majority vote. We are taking odd numbers because we don't want any tie in the voting process. Now, if we take K equals 3, that means after taking all the distances, we'll take the first 3 distances, and these distances will have label with them. and then we'll take a majority vote. So maybe D1 will be, suppose we have an image for 3, and D1 may be shortest distance for a 3, D2 may be shortest distance for a 3, and D3 may be shortest distance for a 8. In that case, we'll get 2 votes for 3, 1 vote for 8, and then we'll consider it as 3. Basically, we'll take it as a 3, and 8 will be discarded. So it will be a correct classification, but we are taking majority vote. Similarly, we can take 5 neighbors. That means after taking all the distances, we'll sort them, take the top 5, and let them vote. So basically, the steps are: find distances, sort them, that means the distances, take top k based on this k, take a majority vote, the majority wins. The majority level wins. So now this is the process basically. Any questions? Is it clear?
Yes, sir.
So now if we want to decide which K is best, so can you comment based on the result here? Anyone? What do you think?
K equals 3.
K equals 3 is best here. For example, here, this is the error rate. So the lower the better. So we understand that for K is equals 3, the error rate is the lowest. So this is the best. But what about the trend? Can you comment on the trend? Can you find any pattern from the trend? Like
Like increase করতেছে then decrease করতেছে এরকম।
It's true, it's increasing and decreasing, increasing and decreasing, but what feelings do you get from these numbers? So basically, we see that if we take only one neighbor, that means K equals 1, we get an error of 3.09%. If we increase the number of neighbors to 3 and use majority vote, the error drops to 2.94, and then error increases again, even more than K equals 1. If we take more neighbors, error drops a little bit, and then increase again, drops a little bit, and we see the trend. Maybe it will increase again. But the thing is, for 3, it is working best. So now we may have some confusion, like why is that the case? If we use more, normally it should be better. But we see that if we use more, it's not really the better. So the problem here is if we use majority vote, the majority vote sometimes confuses the algorithm. So maybe at some point we'll see that if we use maybe 7 nearest neighbor algorithm, for 3, maybe we'll have 8 levels and 3 levels. So there are 3 levels for 3, there are 4 levels for 8. And based on that, we'll classify 3 as 8. So if we take majority vote, it does not mean that it will be better always. Maybe it will confuse the algorithm even more. So that's how we got it from here. So it is not that this k nearest, if we increase the k, it will be worse for any data set. It's not true. This table only is valid for mnist digit data set. So for mnist digit data set, and if we use k nearest neighbor algorithm, then for k equals 3, it works best. But for other data set, it will be different. Or maybe for other data set, k equals 11 will work best. Maybe for other data set, k equals 5 will work better best. Or for some other data set, k equals 1 will work best. We do not know. So these algorithms change their behavior based on data set. So we'll study other machine learning algorithms too, and we'll see that we need to somehow find out which algorithm with which parameter works best for a data set. For example, for mnist data set, if we use k nearest neighbor algorithm, she will work best. Maybe we'll another algorithm. But if we decide that we'll use nearest neighbor algorithm, then three nearest neighbor algorithm will be best for this data set. So how can we really test the parameter of an algorithm formally? So we'll have separate classes for model selection, but because this is the first class and we want to get an idea about the total machine learning process, we'll discuss it a little bit. So it's part of model selection. And an algorithm has many different parameters. We need to find out which parameter works best for the data set. For example, k nearest neighbor algorithm, the parameters are the values of k. Now, if we want to find out which k works best, how can we do it? So basically, we need to find out the accuracy. So accuracy for k equals 1, accuracy for k equals 2, or in the same argument, accuracy means 1 minus error rate. So we can even find error rate. So error rate for one nearest neighbor algorithm, error rate for 2, error rate for 3, and sorry, error rate for 1, error rate for 5, 3, and so on. Now, how can we say that those error rates are representative values? So for that, we use cross-validation. Cross-validation. Even the cross-validation, we can be parameterized in different ways. For example, we can use 10-fold cross-validation. So if you use 10-fold cross-validation, we start working from our training set. For example, here, for the training set, we had 60,000 images. For the test set, we had 10,000 images. Now, if we want to use cross-validation for k nearest neighbor algorithm on mnist digit data set, and if we want to use 10-fold cross-validation, then we need to divide the training set into 10 different pieces or chunks. So 10-fold cross-validation means our training set will be divided into 10 different chunks. And our dataset, our training dataset will be equally divided into these pieces or chunks. So the first piece will contain maybe 6,000 images, because 60, 10 cross-validation. So each piece will contain 6k images. And the second chunk will contain the next 6,000 images, and so on. And the last chunk will contain from 55,001 number image to 60,000 image. So last 6k images. Now, particularly for this problem, what we'll do, we'll number the chunks. This one, S2, S10, and then we'll find error for the chunks. So what we'll do, for S1, these 6,000 images will be separated here. All the 6,000 images. What we'll do, take 1, 2 until 6,000 image from here. So we are taking all the images one by one, iteratively, and we'll try to find a label for this image from the rest of the training data. So we'll get an image using whatever algorithm we want. Maybe one nearest neighbor at first, then three NN second, then 5 NN third, so on. And we'll compare if the return label is correct or not. And we'll do that for all the images of the first chunk. And then we'll find an error rate. And this will be the error rate for the first chunk. And for the second chunk, again, we'll take all the images iteratively one by one, 1, 2, until 6K. And from the total image set S, we'll remove all the images of S2. So from this set, that means we'll have everything other than this chunk. And then we'll find a label of all those images of S2 from the rest of the data set and compare with the known label. And then again, find another error rate 2. And we'll do that for all the pieces and take an average. So this will be the error rate for an algorithm of KNN for different K. And that's how we got the values of these K values. So for this is 1 NN, this is 3 NN, this is 5 NN, this is 7 NN, and basically we find these error values using tenfold cross validation. Any questions? Is the process clear? This is customized for nearest neighbor only. Normally the cross validation works in a little bit different way. I hope it's clear now. Now, what we are really doing here is matching images. Now, matching images using nearest neighbor algorithm and distance metric is really hard. But we saw that the algorithm performed not bad. We said that performance is really good, but we can do it even better. For example, we can use some image matching specific algorithms. For example, rotation and translation invariant algorithms like tangent distances, or using shape context. They are defined mainly for finding object similarity. So if we use them as a distance metric, then the accuracy of the algorithm increases even more. For example, if you use tangent distance, the accuracy becomes almost 98.9%. And if we use shape context, it's even more than 99%. So nearest neighbor algorithm, basically how it will perform, it depends on what distance metric we use and for what kind of data set. For example, for image type of data set, we need to find distance that makes sense for images. For example, if we have a 1 here, and if we shift the 1 even by a couple of pixels values, for example, this is 1, we are shifting here to here. Now, for the translated image, if we take a distance, the distance will be huge. For example, here, the pixel value is 255. Maybe here, the pixel value is 0. So if we take a distance, even if they are 1, but shifted a little bit, the distance will be huge. Similarly, if it's 1, maybe someone wrote a 1 with a little bit more slanting, like this. Even then, if we take a pixel value from here, it will be almost 0. If we take a pixel value from here, maybe it will be 255. So what we'll do, 255 minus 0 square plus something and then take a square root, but the distance will be huge, even if the content is same. So for that, we need to find a distance metric that can understand that this pixel is same as this pixel. Also, this pixel is same as this pixel. So tangent distance can understand better than Euclidean distance. That's how we see that error accuracy improved from almost 97% to 98.9%. Shape context, it can understand even more. It operates on chunk of pixels, like couple of pixels together, and then define some shape with them. And based on the shapes, it can find object similarity, basically. So, or on the other, also, we can tell it that it can find the distance between similar objects. And because it is basically translation and rotation invariant, we can see that the error rate even drops more and the accuracy improved. So if we want to classify with more accuracy using nearest neighbor algorithm, we need to find out a distance metric for the data set we are using. Now, what are features? So here the features are just the numbers. For MNIST digit recognition problem, the one-dimensional vector that we created from the image, all the numbers, each number is a feature. Each number is a feature. That's why we are saying that we have 784 features. And these 784 features will have a space of 784 dimensions. So each dimension is a feature, and we represent the feature using a number. Now, if we use more feature, can we say that the algorithm will always perform better? For example, here we are using just one feature. There are two classes, red classes and blue classes. Now suppose suddenly we got another feature for the data set. So another feature, that means now our data set will be represented using in two-dimensional space. So that's what we are doing here. Now, if we run nearest neighbor algorithm on the data set using two features instead of using one feature, we see that now for this pixel, the nearest neighbor is this. So basically, the nearest neighbor for the red class is now a blue class. So maybe this will be classified as blue. On the other hand, if we use only just one dimension, then for this point will be really, really closer. Here and here, here and here, just very close. But after using another feature, this red class maybe will be classified as blue class. So if we use more feature, we cannot say that our algorithm will always perform better. So our algorithm will perform better if we have relevant features, not features like these that can mislead the classifier. So, so for this problem, maybe it's not a huge issue, but for most of the machine learning problems, we need to be careful about the features. One of the bottleneck of this algorithm is sorting or finding the neighbors. Now we know that sorting normally works in n log n, and then we need to find out the distances, the top k distances. So we need to be careful. We need to be careful, and also there are some other algorithms too. So if we really need to use nearest neighbor algorithm, then we can use these algorithms as helper. So all of them will help us in doing everything in logarithmic time, then linear time, basically. So naive, even naive search, they will take order of n. But if we use these algorithms, they'll all they will all change the time to some sort of logarithm. Maybe not just 10 base logarithm or 2 base logarithm, maybe other base logarithm, but they will be reduced to some logarithmic order, not in linear order. We'll talk about distance metric a little bit and then metric space. So metric space is the general term. So what we really need to define distances in nearest neighbor algorithm. So first one is Euclidean distance. We already discussed about it. So in 2 dimension, we define it like this. So we take the distance with in all the axes, take their square, sum them up, and take square root for L2 in 2-dimensional Euclidean distance. We can generalize it to P LP. Then we, instead of taking the square root, we take the pth root. So for all the axes, we use pth power and then take the one of them pth root or pth root basically. For 2-dimensional space, this converges to taking square and square root. Now we'll check 3 different cases of Euclidean distance: 2 extreme, L1 and L infinite, and then mostly used one, L2. For example, we have a vector now. If we want to find out L2, the most common distance, it will be like sum of xi square root. So it will be basically, suppose you want to find the distance from the origin point. To take distance from the origin point, then it should be like so basically in L2 it will be root of d, because for all the axes we'll have 1 minus 0 1 minus 0, because the vector is 1 1 1 1 1 and we are trying to find distance from 0 0 0. So for all axes we'll get 1, and because it's a d-dimensional space we'll get d ones. So basically root of d. Now L1, it is sum of the absolute values. So now it will be d plus d so it is 1 plus 1 plus 1 d times, basically d times it will be d. So for L1 it is d, for L2 it's root of d. Now L infinite. L infinite is defined in a different way. It's, I think, also called Chebyshev distance. So it is defined as the max of any axis. So it will be max of any axis. Now we know that for all the axes the distance is 1, so max should be 1, so L infinity is 1. Now we'll do a reverse problem. So we are considering only two-dimensional space. We want to draw all the points with L2 length 1. That means we want those will be the points in the circle, because for the circles L2, that means A square plus B square root 1. So in other words, we'll have a 2-point D1, D2 from origin 0, 0. So D1 square plus D2 square root. Now for L1, the length is 1. So L1, we define L1 as sum of xi minus zi absolute value. Now absolute value should be so they will have absolute value means we will take either plus or minus for the for one axis and similarly for another axis, and we'll connect them. So all of these, all of the data points in the boundary will have a length of 1. Even if we take from here, this part will be called this part. So there will be 1. Now L infinity equals 1. That means the maximum is counted only. So all the maximum is counted. So if we check, you can see that for L infinite only the max is counted. So all the points for x equals 1 or x equals minus 1. For all the points y equals minus 1, y equals 1. That means all the points in this boundary. Okay, I'll give a 15 minutes break now. After that, we shall continue nearest neighbor algorithm, and then we'll go to probability analysis. Okay, now a 15 minutes break. So the more general form for any distance metric for nearest neighbor algorithm must follow these rules. That's why they're called metric space. So if any distance metric that follows all these rules can be used for nearest neighbor algorithm. So they are basic simple rules. The first one is non-negativity. So the distance must be non-negative, and distance should be 0 only if x and y are same, and the distance from x to y should be same as distance from y to x, and they should follow the triangular inequality. That means direct distance from between 2 points, it must be smaller or equal if they go through another point. For example, the LP form, they follow all these rules. We can give example using Euclidean distance, or p equals 2. So the distance is sum of x and minus zi square root. Now, if we check the distance is always non-negative. So we're using some numbers, square of some numbers, they are always positive, and we are taking the square root. And the distance from x to y is 0 if and only if x equals y. You can see that it's true. If here x and z are same, only then we'll get 0 here. And this must be true for all the x's. That means for all the x's, the x and z value should be same. x1, z1, x2, z2. That means they're basically the same point. Similarly, they're symmetric. We are not taking anything from any order. We are just taking the difference and making it squared. So if we swap the values of x and z, we'll get the same values. And finally, it also follows the triangular inequality. We can check this even for other metrics that we may not think as metrics. For example, the edit distance. So you're familiar with the edit distance algorithm for strings. For example, if we have a string like A, C, G, T, and a string like C, G, A, T, maybe the letters used for genome sequence. So we can check the distance, edit distance, like how can we get this destination string from the source string. So for all the strings, we use the different update, swap, or delete different operations. Now for this edit distance metric, so it will provide a number. It will provide us just a number, like how many edits do you need if we want to get the destination string from the source string. And now we'll get a number from this algorithm, and whatever we'll get, it must be we know that it is a positive number. So the first property is checked, and second property is the edit distance will be only 0 if the source and destination string they are same. Again, they follow the symmetry rule because the number of edits required from going from source to destination will be same as the number of edits that we need to go from this destination to the source. And also they follow the it also follows the triangle inequality. That means we can use edit distance. That means we can use Nares-Neville algorithm for string matching or string similarity, these sorts of things. Sometimes we use Nares-Neville algorithm for distance metrics that does not follow all the properties. For example, the Kullback-Leibler divergence or relative entropy. We call it normally KL divergence. So it measures the distance from one probability distribution to another probability distribution. So this metric, it does not follow all the metric space properties. For example, if we check, the first one is non-negativity. It gives us positive values. It follows this property, but none of the other properties. For example, distance of x equals 0 if and only if x equals y. I think also this is followed, because if we have p and q same, then it will give us log of 1. So it will give us 0. So also the second property, it follows the second property, but it does not follow the third and fourth properties. For example, for symmetry, we see that we have two distributions, P and Q, and they are used in a different way or in an asymmetric way in the equation. For example, we are using Px, then Px in the upper of the as the numerator and Qx as the denominator. So basically, this the equation is asymmetric. So that means distance from P to Q will not be the same as distance from Q to P. And also triangular inequality does not really make any sense for this metric. So it does not follow all the properties for metric space, but still it is used and it gives us very good results. So it's an exception, but it gives us good results, and there are some reasons for that. The first, the most important reason is for finding distance between two probability distribution, we do not have many metrics. So basically, we have to use this matrix if we want to find distances in different distributions. Now, what do we mean by distance between distributions? We can give an example for that. So one distribution could be P. So distribution means how the probability values are distributed over the values. So maybe one distribution is P. The probability values for 4 different elements could be half, 1/4, 1/8, 1/8. So if we add them up, we'll get 1. There are 4 different values, and the probability values are distributed in this way. And Q could be another probability distribution, and the probabilities are distributed this way for the 4 different values. And again, they add up to 1. That's why it's a distribution. Now, if you want to check the distance from P to Q for these two distributions, P to Q, we'll do it this way. So Px log Px divided by Qx. So half log half 1/6 plus 1/4 log 1/4 by 1/3 plus 1/8 log 1/8 1/3 plus 1/8 log 1/8 by 1/6. Now we can easily check the distance from P to Q is not the same distance as Q to P. For example, these values, they will be changed. The numerator will be denominator, and denominator will be numerator. So the value will change. But this metric only follows 2 properties. It always gives us positive values, and it will give us 0 if and only if, or not the if and only if P and Q are the same point. Then we'll get 0. So this is our last slide for a nearest neighbor algorithm. If you have any question, you can ask now. Any question? Oh, can you please repeat the question?
Sunset X distance of 2 seconds.
Did anyone understand his question? Because I think maybe I have some network issue. But did anyone of you?
So many expected distance declared for 7. Expected distance 1/2 or 1/4.
For the last slide, for the scale divergence. Sajid Hussain, are you talking about the last slide, the scale divergence entropy?
Yes, sir. Yes, sir. 24th slide.
24. Okay, so here we are trying to find distance between two distributions, two probability distributions. So it's defined. For some data set, we'll be able to define probability distribution, especially for some generative models. So we want to find a distribution that can generate data for specific kind. Now, for those problems, we start from some initial distribution and try to find the correct distribution. Then we need distance between two distributions so that we can find the correct one. The closer we are to the correct distribution, we get less and lesser distances. So for such problems, we use KL divergence or relative entropy. And then we need to find distance with another distribution and somehow find something closer than the previous one. Again, closer than the previous one, until we get a distribution that really close to the correct distribution. But if we want to do that, we need to somehow measure the distance. And relative entropy or KL divergence can do that. But it does not follow all the properties of metric space. But still, from our experience, we know that it always works. I really didn't understand your question properly, so I just explained everything again.
Yes, sir. It's clear.
Okay, then if everything makes sense to you, then I'll start our next topic. That means the properties of probability. Okay, no questions. Okay, I'll start the next topic. So we'll revise some of the concepts of probability. So basically, we'll review these topics: how to define probability space for an experiment where the outcomes are random, how to formulate an event of interest, the probability that two events both occur together, conditional probability Bayes rule. Today, maybe we shall discuss until we'll discuss this, Bayes rule. What is a random variable? Expected value variance until this point, and in the next class we'll start from here. And in the next class we'll finish the probability review, and we'll also try to finish the basic concepts of linear algebra that we need for machine learning. Again, I think you already know these concepts, but still this is probability. So I think for many of you, you need some brush up. So that's what we'll do in this lecture. Again, I cannot see some of the steps. So do you see any slides here, or is it just an empty slide?
No slide, sir. Empty slide.
Empty. Let me reload it. Sorry for that. So we'll cover until variance and standard deviation. So first is we are all familiar with this problem. If we roll 2 dice, we roll 1 dice, something like that, and then we have a question like, what is the probability that they add up to 10, or what is the probability of this? Now, for solving this type of problem or any probability problem, the first step is to find a sample space, and then the probabilities of outcomes. So what is a sample space? For example, if we roll 1 die, sample space means what can we expect to see? We can expect to see either 1, 2, 3, 4, 5, or 6. This is a set. We only list any outcome only once. So this is a set. And normally we use omega to represent. So this is the sample space if we roll just 1 die. What about if we roll 2 dice? Then we'll have a sample space like that. 1, 2, 3, 4, 5, 6. Sometimes even we use a notation like this, 5, 6 square, or sometimes even in elaborate form like 1, 1, 1, 2, 1, 3, 1, 6, 2, 1, 2, 2, 2, 6, until 6, 1, 6, 2, 6, 6. So we're listing everything here. So this is our sample space. That means what could be any outcome. So all the outcomes that are possible will be in the sample space. Now the probabilities of outcomes summing up to 1, that means probability of all the outcomes, or maybe we can say it in a different way. Like what will be the probability that we'll see any of the outcome? Probability is 1. That means we can only observe these things and nothing else. So that is what we mean by probabilities of outcomes summing up to 1. That means probability is 1 that we'll see at least any one of them. So sample space contains all the outcomes that we can expect. So we represent probability space using sigma, all possible pairs of the dice rolls. And now, what is event of interest? So we define event of interest on the sample space. For example, event of interest could be the 2 dice add up to 10. Now the event of interest, they will contain subset from the sample space. So the event will contain subset from the sample space. For example, here we are talking about 2 dice adding up to 10. That means the event that matches this criteria should be 5, 5, 6, 4, and 4, 6. So these 3 outcomes, they conform with this criteria. So our event of interest will be 5, 5, 6, 4, and 4, 6. And probability of this will be the total elements in this set and the number of elements in the sample space. So 1 by 12. So this is event of interest A. This is the probability of the event. Most often we are not interested really in one event. We are interested in multiple events. And in machine learning, basically we try to solve problems with multiple events. For example, a doctor may see a patient, and the doctor is taking the patient's temperature and blood pressure. Now, these are two events. There is a sample space for that. What are all the temperatures a human can have, or the blood pressure that are possible for a human? So there are some sample space. Now the doctors take sample for a patient from the sample space, but the doctor is not really interested in either temperature or blood pressure. Maybe he is interested in particular disease, maybe a heart disease, maybe kidney failure or something. So basically he is taking some vitals, temperature, blood pressure, a sample of this metric from sample space for any human, and the doctors are interested in finding another disease. So basically, the doctor is taking two events and trying to find out the probability of the third event. So the first event is taking particular blood pressure. Second event could be the doctor is taking temperature. The third event, maybe patient has a disease, and the doctor is trying to find a probability of having that disease. For example, the doctor can say that the patient has a artery block with certain probability, may have kidney disease with certain probability. So basically, they are interested in measuring another event based on some previous events. So if we want to use probability for machine learning, basically we need to be able to find out events based on other events. And for that, we use different conditioning, Bayes rule, all these things. For example, there are two events A and B. We want to find out event B, and we can observe event A. So for example, we can observe blood pressure, we can observe temperature. What is the probability based on those events that another disease may happen? So we want to find out numbers like this. We're interested in finding this kind of metrics. But how do we do it? So for that, we use conditioning formula. Conditioning formula means what is the probability that two events happen together? For example, event A and B, what is the probability that they will happen together at the same time? So for that, we can use a formula like this: probability of A and B. Use a formula like this. That probability of A and B will be equal to probability of A, and then whenever probability happens, what is the probability that B also happens together? Or we can rewrite it in a different way. Probability B happens, and then what is the probability that A happens with B? That means probability of A given B already happened. And in this case, probability of B, at first probability A happened, we know. Then what is the probability that B also happened? So if we combine these two, then we can find this value. And we can, this is a homework problem. So you need to solve it using this conditioning rule and Bayes formula. So the problem is like that. There are 10 points. I'll discuss the solution in the next class. So there are 10 points, and among the 10 points, 9 points are paired, and 1 is a bad point. Now we randomly picked. So there are 10 points. We randomly pick a coin and toss it 4 times. And we see that all the time it is giving us tails. So the 4 toss all gave us 4 tails. Now the question is, what is the probability that we picked the bad coin. Now, if we pick a good coin, the probability is low, but it's not impossible to get 4 tails in a row. It is possible, but almost improbable. So we need to find out what is the probability that we pick bad coins. Probability of we picked the bad coins given we got 4 tails in a row after picking the coin and after tossing it 4 times. So find out this probability and we'll discuss the solution next class. Now, the Bayes rule, we can use Bayes rule to find out a probability like this. So Bayes rule, using Bayes rule, we can find the probabilities that are difficult to find. For example, maybe we want to find out probability of A given B. So basically, we have some symptom. Going to find out cause. Now we can think that we can find that using Bayes rule, but we can find the Bayes rule is from the conditioning formula. For example, probability of A and B. We can rewrite it in a different way. Probability of A given probability of B given A. Or we can write it like this: probability of B times probability of A given B. Now from here we can find probability of A given B. So probability of A given B should be probability of A into probability of B given A, then probability of B. Now we see that if we want to find this, we can use a formula like this: probability of B given A into probability of A divided by probability of B. Now we want to find out a cause for the symptom. Now here the things are reversed. So we want to find out symptom, that is the cause. Now we say that it's easy to do. So if you already know the cause, then find out symptoms is easy. But the reverse is not easy. So when we encounter situations where we find some difficult to find probability, but the reverse is easy, then we use Bayes formula. So like it's called basically here kind of symptom. From the symptom, we want to find out the cause, but the probability space is larger for that. On the other hand, when we already know the cause, we know what will be the symptoms. So that means we can take advantage of what we know to find out the difficult, to find out solution to difficult problem, and we want to find out what is the cause. So sometimes it's called prior.
So একটা student maybe wait করতেছে.
So sometimes I admitted him. So sometimes we call it prior. Basically, that means it's a prior knowledge. So we know the symptom for causes, and then use our observation, basically to find out the difficult solution to difficult problems, like finding probability for a new disease. Now, what is random variables? Normally, we use a capital symbol to denote random variable. So random variables are variables that can map our sample space, portion of the sample space, to some numbers. So basically, it's a mapping. So when we say mapping, that means random variables are basically kind of functions. So that can map part of this or whole of the sample space to numbers. For example, we have a sample space. That means we are rolling 2 dice. And now, if we talk about the sum of the 2 dice, so X will have values from 2 to 12, because the combinations will start from 1 1 to 1 6, and it will end from into 6 6 6 1. So the values will start from 2. Some numbers will be repeated, but because it's a set, we have every number just once, and the maximum number will be 12. So here, when you say that X is their sum, that means X is a random variable that maps the entire space into these numbers. So here we are saying we are giving it a name variable. Actually, it's a kind of function. So for a definition, we can use this. So a random variable is defined on a probability space, and it's a mapping from all the outcomes to some numbers. So basically, it's a function. Now, what is the distribution?
একটা student may be disconnected.
I can't see anyone disconnected from here, or no one is in the queue. The waiting queue is empty, so I cannot see anyone there.
Maybe join করছে.
Okay. So now, what is a distribution? So distribution basically tells us about how the sample space is distributed over the numbers. So that's why we're talking about distribution of a random variable. So the distribution of a random variable. That means that what is a random variable? It is defined on the sample space to a set of numbers some portion of it, random variable X. Now, when you say distribution of a random variable, we are really talking about how this sample space is distributed over these numbers. So that's why we see normally a number like this. So there are some numbers. How are the numbers from the sample space are distributed over this region? So it is called distribution of a random variable. For we have an example here. We have an example here. So here we define X equals 1 if a die is greater than equals 3. That means like that. 1, 2, 3, 4, 5, 6. Now X equals 1 if die is greater than equals 3. Otherwise, it's 0. So this is the distribution. Or if we want to look it more like a histogram, we can do like this. 1, 2, 3, 4, 5, 6. So here it's 0, otherwise it's 1. So basically distribution means what percent of sample space are distributed are distributed how over the numbers that we want to map using the variable. So there are two things. So portion of the sample space and the outcomes. Outcomes mean the values that this random variable maps to. So for example, here, random variable x, it is mapping to these values. So these are the values, and this is the sample space. So what portion of sample space are for this number, what portion is for this? So the distribution will tell us that. For example, here, if we check for 2, maybe just one number. For 3, either 2, 1 or 1, 2, maybe 2 numbers. For 3, we'll have 2, 1, 1, 2, again 2 numbers. Sorry, 2, 3. For 4, we'll have 2, 2, 3, 1, 1, 3. So we'll have 3 numbers. So it will have a curve like this. And we call it the distribution for this random variable x. So we have distribution for random variables, not sample space. Now we'll talk about expected values or mean. And again, this is defined for random variable. So we are trying to understand a random variable. So the expected value or mean or random variable is defined using this formula. So it is the expectation, it is the summation of the value of the random variables multiplied by their probabilities. For example, if we roll a die and x be the number observed, what will be the expected value for the for this variable? So this variable can have values 1, 2, 3, 4, 5, 6, and the probability values associated with them will be 1, 6, 1, 6, 1, 6, 1, 6. So the expected value will be 1 times the probability value. So this is the random variable times its probability, the value of the random variable outcomes, again value of the random variable, and so on. So it will be basically 1 plus 2 plus 6 divided by 6. (21 by 6). 3.5. So the expected value for this random variable x is 3.5. Now suppose we will do another example. Suppose you have a biased coin. You have a biased coin. The probability of head is p. So that means the probability of tail will be 1 minus p. Now x is the random variable. It equals to 1 if the coin shows up head, and the value of x 1 or 0. 1 with probability of head, that means 1 with probability of p, 0 with probability of 1 minus p. So for this random variable x, we have 2 outcomes, 1, 0, which is set, and these are the probabilities. So what will be the expected value of this variable? Random variable, that means x, probability of x, and sum over all the values. So we'll have 1, probability of p, 0, 1 minus p, basically p. there are some properties of expected values. So what happens if we double the number or increase the number? Basically, what happens if we multiply or add? So if the random variable is x and we define another random variable based on x, we multiply the random variable x with some numbers and add some numbers. So what happens with the expected value? Basically, if we do that, we can just derive it if you want. It's a homework. But if we do that, then the expected value changes like this. So if we define a variable like this, the expected value will be multiplied by a, and b will be added. So if we have variable x and a variable x, and we calculate its expected value, and we define a new random variable based on x, then we can find the expected value of the new variable without going through the whole process, just using this formula. Another important concept for random variable is variance. So one important concept is mean or expected value. Now we really want to understand the random variable using mean or expected value. So if we check our concept, a random variable x, it maps some sample space to some numbers. That means it will give us some numbers, a range of numbers. Now we want to understand the random variable using this range. So one way to understand is to use mean or expected value. But then the question comes, is the mean or expected value really representative of the variable? For example, here we see random variable x has two different distributions. It is distribution 1 and distribution 2. Now for distribution 1, this is the expected value. And for distribution 2, the expected value is same, mu. Now for distribution 1, most of the values of the sample space are around the mean value, most of the values. On the other hand, for distribution 2, we see that most of the values are not around mean, but they are distributed over a very large region, very large range. So we can find the sense of it using the metric variance. So variance will tell us how the values for this random variable are distributed around the mean value. So mean is one representative. How good is it? We find it using variance. That means we need to calculate basically this number. So we find the expectation of the values around the mean. So we are using expectation. So we are finding the variance of random variable x. How? At first we find the mean value, and then we check the other values of all other values of this random variable. How closely are they with respect to the mean value? If they are very close, then here mu is a very good estimate. If they are not close, they're distributed over a large range, then the mean mu is not a good representative. And we use this formula to calculate variance. So variance has some properties. For example, we see that we are using expectation, and expectation means x, probability of x, and sum. And here, where probability value, they are always positive. And random values, here we are using the square values. That means they are always positive. That means variance is always positive. Now, if we similar to the previous example, where we define a new variable b with respect to x, if we change it like this, we do not need to calculate another variance for b if we know the variance of x. This will be the variance of B. Now, if we add a value with all the values of X, that means they are not really changing the shape of the distribution. That's why we see that we do not have B in the variance. But if we multiply, they are changing the shape of the distribution, and we see that they change. The variance is changed by the square root of this amount. To calculate variance, we can use two formula.
So summary it up at full.
I don't understand what.
Can you repeat the summary?
This one.
Yeah, this slide. Yeah, this slide.
Okay, so basically what is here are the properties of the variance. So the first one is variance is always positive because we are taking expectation of this content. This content, it is a square value, so it's always positive. So here, this content is always positive. Probability value always positive. So you are multiplying two positive content or two positive numbers, and then adding these positive numbers. So basically, we get always a positive number. And then we're saying that if we know the variance of random variable X, and we define another random variable with respect to X, that is B equals X plus B. So we are changing the scale and position. And if we do that, then we can calculate the variance of the new variable using this formula. So we argued that if we add the same value with all the values, the same value will be in the mean value. So basically, if we add all the B values here, the mu will be changed to mu plus B. So all the values are added. So values will have like xi plus B minus mu minus B. So we'll discard the B's. That's why we do not see B in the variance. But if we multiply the values, we'll have like A xi minus A mu square. That means A square xi minus mu square. So that's why we'll have an A square out and then the variance of X. So that's why you see a quantity like that. Clear now?
Yes, sir.
We can also calculate the variance using a shortcut formula like this. Sometimes it is easier to calculate using this formula. We can see one example. We define a X, random variable X, uniformly at random from 1, 2, 3, 4, 5. So that means we have values 1, 2, 3, 4, 5, and their probability values, it is uniformly distributed. That means probability value will be 1 by 5, 1 by 5. So the probability value, this is the values of X. Now we can use this formula. So you find that X squared 1, 4, 9, 16, 25. Now expectation of X squared, probability of X squared, that means 1 plus 4 plus 9 until 25. It's 4 plus 9 plus 16 plus 25 divided by 5. 5 by 5 equals 11. Now mu square. Mu equals 1 plus 2 plus 5 divided by 5. 15 by 5 equals 3. Now, if you want to find the variance of x, expectation of x squared 11 minus mu squared 9, variance will be 2. And if we use this formula, we'll see that the variance will be same. So I'll stop here today. Now I'll call your names. If you have any question, you can ask now. Otherwise, I will stop the presentation.
Sir, I was present last class, but during attendance, my internet connection went away.
We'll talk about that later. So do you have any question about our course content now? Today's lectures or anything? Any question based on today's content? I hope you understood. I'll stop the presentation now.